Good day, class. Let us now continue with our lecture. In physics, you learned that for rectilinear motion with constant velocity, displacement is simply equal to average velocity times time. Or in general, final position is equal to initial position plus average velocity times time. Take note that if the velocity is constant, average velocity is equal to its velocity at any instant, including the initial velocity. Instead of writing this velocity into v sub ave as average velocity, it is commonly practiced to write it this way because this formula is commonly used for problems with constant velocity. However, keep in mind that although it is commonly used for problems with constant velocity, you can also use it for motion with constant acceleration as long as you only input the value of the average velocity for variable v in this formula. In other words, v in this formula represents average velocity, and this formula is applicable only when the velocity is constant or the acceleration is constant. Next, for motion with constant acceleration, we have the following equations. To understand equations 2, 3, and 4, it would be better to derive them one by one. Please take note carefully or pay attention on the derivation process so that you will avoid having trouble applying these formulas into different situations, especially problems from our future topics. Now, let's start with equation 2. Previously, you learned that average acceleration is equal to change in velocity over change in time. But when the acceleration is constant all throughout the motion, acceleration at any instant is also equal to average velocity. Therefore, acceleration is equal to final velocity minus initial velocity all over final time minus initial time. Usually, initial time is set to 0. This means that we can simplify this equation as follows. And then to further simplify this equation, you may cross multiply, giving you this form. Finally, by transposition, you can obtain the second kinematic equation. Just a reminder, when the acceleration is varying, equation 2 is not applicable. This is because during the derivation process, what we consider is a constant acceleration. This time, let's derive the third kinematic equation. Let's begin by taking note that from the first kinematic equation, final position is equal to initial position plus velocity times time. Or you may write it also in this following form by just emphasizing that the velocity in the formula can be expressed as average velocity that is applicable also for motion with constant acceleration. This follows that the third kinematic equation is only applicable for motions with zero acceleration or constant acceleration. When the acceleration is constant, we can use this another formula for average velocity. And to visualize the use of this formula, let's consider this graph of a motion in where acceleration is constant. Take note that this graph is velocity versus time. The previously explained formula of average velocity, which is delta x over delta t, is the general formula and is based on a position versus time graph. In this graph, you can observe the constant increase of velocity as time increases. Let's say we are given an initial and final conditions to consider. To get the average velocity, you simply have to get the arithmetic mean of the two given velocities applicable in this velocity versus time graph. This follows that you may use this formula as long as the acceleration is constant. Now let's substitute average velocity into the first kinematic equation. This gives us this equation. Thus, final position is equal to initial position plus this formula of average velocity when acceleration is constant times time. Then replacing final velocity using equation 2, we express the equation now as follows. Then by simplifying the numerator, final position is expressed in this form. Lastly, we modify this quantity into this form, and then let's distribute variable t, giving us the third kinematic equation. Again, same with equation 2. When the acceleration is varying, equation 3 is not applicable. Kindly recall that during the derivation, what we consider is a constant acceleration. So lately, we introduced a new formula for average velocity. The concept of average velocity might cause some confusion later on when we proceed with our advanced topics, especially when the path of motion is not anymore along a straight line. To clarify this concept, let's just quickly insert uh, this topic about average velocity, and later on we will proceed to the fourth kinematic equation. A while ago, you learned that when the acceleration is constant, you may use this formula. But how about for varying acceleration? In that case, use the general formula that we first discussed for average velocity, which is average velocity is equal to displacement over time interval. To see their difference, these two, let's say we have a particle moving with a given initial velocity, traveling this given path until it reaches a particular point, consider as the final position, attaining a particular final velocity. Recall that displacement depends only on the initial and final position. So you can observe here that acceleration is present since both magnitude and direction of the velocity changes. However, for this case, this acceleration is not constant. This irregular curve path will give you an idea that acceleration is varying since the change of the direction of the velocity is not constant as it follows this irregular curve path. There is a point that the particle travel with a, let's say, with a given direction, then changes by a certain amount of angle to attain its new direction, then changes again at some point by another amount of angle to attain another new direction, and so on. Therefore, the rate at which the direction of the particle's velocity changes is varying. Even if the increase or decrease of the magnitude of the particle's velocity is constant, the acceleration is still varying due to the varying change of direction of its velocity. Therefore, you cannot apply this formula. When encountering such problem, just go back to the basic, which is this general formula of average velocity. Now let's go back to the derivation of the last kinematic equations. which is the fourth kinematic equation. Let's now derive this equation by outlining first the needed formulas. Let's recall that from equation 1 we have this formula. Also, when the acceleration is constant, we have this formula. Finally, remember that from equation 2, we derive this formula. Then, by manipulation, we can express time as follows. This time, we will consider equation 1 as the starting equation, and then we will just replace average velocity and time from equation 1. So we will use these two equations. So replacing average velocity and time of equation 1, this gives us this following expression. The following expression of final position. And then by transposing the initial position to the left and simplifying the remaining term on the right, we have this equation. To simplify further, just multiply both sides by 2a to remove the denominator. Then by special product, we can further simplify the equation as follows. Finally, by transposition, we now have the fourth kinematic equation. The same with the third kinematic equation. Take note that when the acceleration is varying, equation 4 is not applicable. So this is also because the acceleration that we consider during the derivation is when the acceleration is constant. Now that you have an idea on how these kinematic equations are derived, you will soon memorize these equations by frequently applying them in problem solving. All these four kinematic equations are only applicable when the acceleration is constant. For sample problems, kindly refer to the next part of this lecture.